Pleasure to be here. As a Coloradan, I'm partial to the mountains back home, but I have to say the mountains and the sea are quite nice. And I've certainly enjoyed other unfamiliar mashups, the bringing together of various communities at this workshop. It's been tremendously educational for me, but I think also fruitful scientifically for all of us. And so I'm happy to be able to take a part in this. I'll start with some motivation and context for thinking about numerical analytic continuation. So in some sense, this is the math problem we want to solve. And what this equation says is that the Euclidean time correlation function, this is the sort of thing we compute using lattice QCD numerically. This is related via Laplace transform to the spectral density rho of omega, where here omega is some kind of energy. And of course, if you had the quantity on the right-hand side, it would be trivial to compute the left-hand side. But in general, it's difficult to undo this, to compute the inverse Laplace transform. It's not manifestly obvious that this particular problem is a problem in analytic continuation, but in the course of the talk, I'll show you why this is true. Before diving into the technical details, I want to motivate a little bit why this is an important problem for people to be thinking about. And I want to do so by going phenomenological. So to do so, let's think about electron-positron annihilation into hadrons. It's an inclusive quantity. And to this end, let's construct a particular observable, the R ratio, capital R of S. So this is defined as the total cross-section from E plus E minus goes to hadrons, normalized by the tree level rate to go into muons. The reason you want to do this ratio is to basically strip off the leading power law decay of this cross-section. If you do this, you've got a perfectly well-defined observable, and experimentalists can measure this. And so a recent summary of the experimental status is here. You see this delightful blue curve with many different peaks. If you like, this is the electromagnetic structure of the hadronic vacuum, and you see the conspicuous peaks from the rho, the omega, the phi. You see the shoulder from the rho prime, and then other very sharp peaks as we move above the threshold for various charmonium resonances. So that's just purely the experimental situation in terms of this observable. If you invoke the optical theorem, though, and you think about this as not an experimental cartoon, but a Feynman diagram, you can relate this process to a non-perturbatively defined correlation function defined in QCD. And because cross-sections go like the square of diagrams, it's basically an electromagnetic current-current correlation function. And because we're probing the vacuum in this, we've got vacuum states on externally. So this is a creature that has two Greek indices. If you strip those off in the usual way, what you're left with is a scalar function. That's the scalar function that I'd invite us to think of as the spectral density. And up to some conventional normalization factors, this basically is the R ratio. So given such a beautiful experimental curve with so much structure, a perfectly good theoretical question to ask is, how much of that curve could we produce directly from first principles, starting from the Lagrangian or the Hamiltonian of QCD? So in some sense, that's what we'd like to do. It's not just the R ratio. It turns out similar inclusive observables are related to all sorts of areas of phenomenological interest and excitement. So if we switch from an electromagnetic current correlator to a weak current, so vector minus axial, this is the sort of thing that you could probe in inclusive tau decays. And as the tau decays through the weak interaction, you've got up and down quarks being produced. You've got up and strange quarks produced. So in fact, this is related to the CKM matrix elements VUD and VUS. Now, I don't know that everybody's been following at this, but in fact, there's a slight tension here. It goes under the name of the Cabibbo anomaly. And what that says is basically the sum of the squares of these two, there's a deficit with respect to unity that you'd expect in the standard model. And so this is something that we'd like to understand better. Inclusive B decay. So if we take this current correlation function that you're sensitive to in inclusive tau decays and strap for the external states B mesons on there, you could study inclusive decays of B mesons. This is interesting and exciting because of the long-standing tension between inclusive and exclusive determinations now of VCB and VUB. And parenthetically, exclusive semileptonic decays have long been the provenance of lattice QCD, but it's only more recently that people have begun thinking about inclusive semileptonic decays using lattice QCD. Another process that's very timely given US activity in the accelerator-based neutrino program is something like neutrino nucleon scattering. So here we've just taken this 4-point correlation function and now swapped out the B mesons for nucleons. The deep underground neutrino experiment planned at Fermilab, this is going to be scattering neutrinos off of argon nuclei in the few GeV range, and you have enough energy that you can really produce a wealth of different hadronic resonances. And so it's useful to say, you know, if we could compute this thing fully inclusively from QCD, at least on a nucleon, could you use that as an input into the nuclear theory to try to constrain cross-sections like this that Dune will do. Similar correlation functions are also relevant for transport coefficients in hot QCD. And as I was sitting through Ian's talk this morning on energy correlators, there's probably a similar story there to be told, although I haven't thought it out in detail. So suffice it to say, determining spectral functions from lattice QCD, if and when we could do it, would be an important and impactful problem to think about. Okay, so the inverse problem. Here we are back again at where we started. We'd like to determine, starting from the Euclidean time correlation function, presumably computed using Monte Carlo techniques for lattice QCD, the form of the spectral density, for all the reasons I just explained. Now, what makes this a challenging problem? Well, there are some intertwined conceptual and technical hurdles that you have to overcome. So the first, and we heard some about this already today, is that the calculation in a finite volume actually deforms the spectrum. And so there's something to be said about how the infinite volume observable is connected to the thing you can actually get your hands on. The second is, as a matter of principle, the Euclidean data are available only at a finite set of points. So you have to sort of say what you mean by a solution to this problem. And the third that I've got grayed out, because I won't say much about it today, although it's been primarily what I've been thinking about lately, is the reality that statistical uncertainty is going to be present in any Monte Carlo calculation of the left-hand side. Okay, so let's talk first about the deformation of a finite volume, and this discussion is going to build on Steve's nice talk in the morning. And just to be very concrete, let's think about, say, inclusive electron-proton scattering. Okay, so at low energies, you don't have enough energy to produce anything, so it's electron-proton going in, electron-proton going out. And so if you think about what the spectral function is, it's just going to be a delta function, and then all the dynamics is going to be in an elastic scattering form factor, and it'll go like that quantity squared. As you increase the energy, eventually you'll go above some multiparticle threshold. In the case of QCD, once you've got enough energy to produce a pion, you've got more dynamics opening up, and so here's a step function that says you're above threshold. It's going to open up proportional to the phase space for that process, and then it'll go like the matrix element squared. So that's a cartoon for what we would expect this to look like in infinite volume. But as Steve told us this morning, any quantum mechanical system in a box has a discrete spectrum. So this is the kickoff for the finite formalism, finite volume formalism that he described, often associated with the seminal work of Martin Lucier and others. And in Steve's slide, you saw many, many references to the very many people that are doing excellent work. And this has really been one of the exciting areas in lattice QCD over the past 10, 15 years, where it's gone from really theoretical ideas to practical calculations compared to data. So I invite you to check out those. In passing, I want to say that there is actually an interesting numerical analytic continuation problem that happens at the very end of what Steve described, where you have the scattering amplitude as a function of the energies on the real line, and you go looking for poles or zeros in the complex plane. Coming soon to an archive near you is some work on this that I've been involved with together with Fernando Romero Lopez, who featured prominently on many of Steve's slides, as well as Fernando's excellent postdoc, Miguel, and they're both based in Bern. So keep an eye out for that, although I'll have nothing more to say about that in the talk today. So really what we want to do, though, is we want to connect the infinite volume picture on the left here with the finite volume picture on the right, where you've just got a comb of Dirac delta functions, one at each finite volume energy level. And as Steve showed, if you work hard and do like a GVP calculation, in principle, you might be able to pull off many of these, at least at low energy. But what's really the connection between these two quantities? How do you reconcile those pictures? There's been a renaissance in people thinking about these, and it really goes back to a nice paper in 2017 by Max Hansen, Harvey Meyer, and a student, Robina. And what they said is, let's smear, right? And somebody, I think, had a question about this after Steve's talk, and so now we'll get to do it a little bit more. So choose some smearing kernel. It could be some narrow Gaussian, and we're going to convolute it with the exact finite volume spectral function here. So as we drag this Gaussian across, it's going to smear everything out, and you'll get something that looks potentially like the cartoon on the right, especially if your smearing width is large enough. And you can see, well, those don't look so different now. And what this does is it then motivates you to define, in a computable way, the infinite volume spectral function as the result of an ordered limiting process, where you always focus on the smeared spectral function, then you first take the volume to be big, so those poles in some sense are coalescing into the multi-particle branch cut, and only after you've done that do you contemplate taking the smearing width to be small, taking epsilon to be 0. Okay, so if we want to do this, right, there should be some algorithm, and what is it that people typically do in practice? Well, a different Hansen, Martin Hansen, together with collaborators Lupo and Tantalo, they published a nice paper that has been what people have been using. It goes by the name of HLT, the HLT algorithm. For those that have thought a little bit about these inverse problems, it's sort of a generalization of the Backus-Gilbert algorithm that appears, for instance, in numerical recipes, but has also been used for many years by the geophysical community, where you're interested in the inverse problem of, how do earthquake sensors on the surface of the Earth tell you something about what's going on the interior? The way this algorithm works is you say, okay, I want a smeared spectral function. Let's suppose I can write it as a linear combination of the correlation function that I have, C of t. And how are we going to determine those coefficients? Well, I'm going to choose some smearing kernel. It could be a narrow Gaussian, and I'm going to try to minimize the distance to that I'm able to get given my data. And so they turn it into a convex optimization problem where the first term is minimizing this distance, and then the second term is kind of a regulator that includes the variance of the Monte Carlo calculation. And as you minimize this convex sum, you've got this free parameter lambda, and you can think about this in the statistical sense as sliding along a bias variance trade-off curve. In terms of the grand conversation of ideas, which in some sense is the subject of a conference like this, there have been elegant connections made recently to Bayesian statistics as well as Gaussian processes. And if you want to go do it yourself, there's a code. Okay, so this algorithm isn't really what I want to talk about today, but I wanted to say something about it in order to show this next slide. And the next slide is sort of an instantiation of the idea from the first slide with the R ratio. So this is a slide highlighting very nice work by the European Twisted Mass Collaboration published in 2023. And let's walk through what the plot is. So in the gray in the background, this is just this R ratio that I plotted earlier. So you've got the peak from the rho and the omega, the phi, and then the shoulder or hump from the rho prime. If you take that experimental data and convolute it with a Gaussian smearing kernel with a width of about half a GeV, what you get are the red data. On the other hand, I tried to emphasize at the beginning of the talk that this quantity is just related to a vector-vector correlation function calculable in lattice QCD. In fact, these are the same inputs that go into lattice calculations of the hadronic vacuum polarization for the anomalous magnetic moment of the muon, which is a big source of activity in our community right now. And so if you do that, if you apply the HLT algorithm, the result of their calculation in the continuum limit is given by the blue points. So a couple things should be said. First of all, it doesn't look too bad, right? I mean, although the smearing width is rather large, so you can't really see the fine features manifest in the gray, it actually looks pretty good. The second thing that should be said is that if you look closely here in the neighborhood of the rho resonance, the agreement is not perfect. The red is slightly below the blue. I forget the the global significance they quoted, it was a few sigma tension, not really enough to get too excited about, especially since I would say this does not have a complete systematic error budget. They didn't worry about QED, they didn't do strong isospin, and neither should they in their first calculation, by the way. But it's nevertheless tantalizing to say, you know, especially given all the excitement around G-2, is this another way that someone could imagine trying to tease things like this out? In other words, the question you might ask yourself is, as a matter of principle, how differential could one go? How small could one make this smearing to try to really resolve those peaks and see if you could really tease out many sigma differences? I mean, Lance had the question today, I think, after Steve's talk, what about the 4 pi stuff? That's something that in the current scattering that Steve described is, I mean, tricky to kind of wrap your head around how exactly you would do it. Somehow, in this way of going fully inclusive, it's just all there automatically. Another way to phrase this question is how much analytic information is there contained in, say, order 100 points, the number of points that you might actually contemplate getting from a lattice QCD calculation. The actual subject of the talk, in some sense, is the ideas that was in this paper I wrote together with undergrad Thomas Bergamaschi, and I'll highlight particularly the contributions of Patrick Orr, a very good MIT graduate student who's now a postdoc at Brookhaven. And to motivate that, I want to give a slightly different perspective on smearing. So at the beginning of the talk, following on this seminal work from Hansen, Meyer, and Robina, we said, well, let's just pick some smearing kernel, right? It doesn't matter what it is, but it turns out, if you think about it the right way, sort of the structure of the problem suggests one for you. And to motivate this, I want to think about a particularly simple Green's function. Just consider a single pole and pick some units so that the pole is located in those units at energy of a half. So here's the complex energy pole, here's the real line, and there's the pole I've chosen. And let's look at the imaginary part of this Green's function for various distances epsilon above the real line. Epsilon doesn't need to be a small parameter here, and so this is the distance epsilon, and you can see right now it's unity. Okay, and if you then look at the imaginary part of the Green's function, that's what I've got on the right-hand side, and you're so far away from the pole that it's very flat and boring. However, now let's bring epsilon down. So down, 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 down we go. And you can see this begins to look like a smeared delta function. And so what this does is it motivates defining a smeared spectral function as 1 over pi, just conventionally, times the imaginary part of your Green's function. This is a nice way of doing things, particularly because it has the benefit of Steven Weinberg having thought of it before me, so it's perfectly reputable. In this classic paper by Poggio, Quinn, and Weinberg, they were interested in smearing for a different reason, namely to connect, quark model predictions to kind of resonance-style physics. So here the motivation is totally different, but nevertheless, it's essentially the same smearing, and probably lots of people had thought about it before, but this is the earliest reference I know. If you say, okay, but what actually is the smearing kernel? Here's what it is. This is sometimes called a Cauchy kernel or a Poisson kernel, and just like a very narrow Gaussian, it's a nascent delta function in the sense that as you take epsilon to 0, integrated against test functions, it behaves as it should. Okay, so how are we making progress on the points that we said we would? Well, I've given the story for how we're to think about the deformation of the finite volume. We're always to think of it kind of against smearing kernels or against suitable test functions, and we want to think about it as arising at the end of an ordered limiting process. Now with this alternate perspective on smearing, I want to tackle head-on this question of how much Euclidean data is actually sitting in those 100, call it, Euclidean data points you can actually do the calculation with. To do so, it's useful to move from Euclidean time, where the calculation kind of naturally happens, to frequency space. So just as a reminder, if you've got a 2-point function in Euclidean quantum field theory, you insert a complete set of states, so that gives you the n. You pull off the time dependence in the Heisenberg representation as usual. You get a decaying exponential, and we've seen these in several plots. We saw it in Will's plot, we saw it in Steve's plot, we saw it in Anna's plot, so somehow this is always what we lattice folks are thinking of. And then there's the exponentially rising term coming from the periodic boundary conditions. If we take this Euclidean time quantity and Fourier transform, if we move to Euclidean energy space or frequency space, the spectral weights come along, and the Fourier transform of this is just a sum of poles, right? On the positive and negative axis, sort of one pair for each energy level. And so the picture you have looks very much like this. The Euclidean data that you started with, this amounts to the Green's function evaluated on the imaginary axis, the so-called Matsubara frequencies of the theory, and the finite energy levels are sitting down here on the real line. This now makes it manifest why this spectral reconstruction problem I've been talking about is actually one in analytic continuation, because given this data up here, you want to infer something about the function elsewhere in the complex plane. And in fact, if instead of being very generic about elsewhere, you just mean a line of vertical distance epsilon above the real line, we should be invited by the structure of the problem to think of this as a smeared spectral function. So it fits the definition of Hansen-Meyer and Robina. Okay, so now's the part where we need to remind ourselves about various basic facts from undergraduate complex analysis. And the first is that if you've got an analytic function, they're defined by a convergent power series in any open set around non-singular points. So in other words, basically whatever I do around here, there are no poles, there are no cuts, there's nothing. So anything that I have that reproduces these red points reasonably well is going to be a good description of it, at least until I run into my first singularity, which of course is that ground state energy level. So if I want to figure out what's going on, out there by the excited states, what this is suggesting is that this is a crummy set of coordinates in which to do the calculation. Okay, let's change coordinates. If you hit this with a Kavli transform, it's a Möbius transformation, a linear fractional transformation, you can map the upper half plane to the unit disk. And to do so, you just take these points and you put them on the real line, and the Kavli transform takes the real line and it wraps it up to the boundary of the disk. This is a much nicer set of coordinates to do things in, because now if you've got some representation of what it's doing, you're now equidistant to all the action, right? All the interesting poles, the singularities, which live on the boundary. So now we can finally give a sharp technical description of the problem we'd actually want to solve. So given some set of Euclidean data, so a set of nodes here in the disk, we want to construct an analytic function on the disk that interpolates those points. And if we can do this, and we can then boldly extrapolate our interpolating function near the boundary, it'll give us access to the spectral function, the smeared spectral function. To do so, we're going to use a corner of complex analysis that, at least from my informal polling of physicists, was not covered in anybody's undergraduate complex analysis course. This corner of complex analysis is old and illustrious and goes by the name of Neven-Linna-Pick interpolation. If you've never heard of it, that's no big deal, because the big idea is in fact easy to state. It's just factor out the things you know, right? So the basic fact that we're going to need is, suppose that I've got some analytic function defined on the disk here, and suppose that this function has a zero someplace. So I take my analytic function g, and I evaluate it at this point in green, which I'm going to call a, and I get out zero, right? That's what I mean to have a zero. So the fact is that you can always write this function g in a factored form. You can write it in terms of a Blaschke factor, which implements the zero, and then a remainder function that's analytic in the disk and doesn't have a zero there. If it's a multiple zero, you just do it a couple times. But if it's analytic, that's all it can be. And you can always write it in a factored form such as this. Okay, so that's the basic fact. I want to point out to people that have done some work in quark flavor physics, of which I know there are some in the audience, that this setup is totally familiar in that setting from the Z expansion of the form factors. Their Blaschke factors, they play exactly the same role here that they do there. They're factoring out known analytic structure of the problem, and this goes back to seminal work in the 90s by BGL and CLN, and so this pops up all over in hadronic physics. Okay, so if you do this repeatedly, it goes by the name of the Schur algorithm, and what the Schur algorithm says is that any solution to this problem can be written as a rational function like this. There are a set of Neven-Linna coefficients, P, Q, R, and S. You can compute these exactly from the input data. There are compact recursive formulas for it. And the thing I really want to emphasize here is the presence and role played by this function f. This is an arbitrary analytic function. You say, wait, this is supposed to be an interpolating formula. Why does it have an arbitrary function in it? In some sense, it's the whole point. What this function does is it specifies, or it gives you the freedom to specify further Euclidean data to constrain your problem. And it plays the role of the remainder function from the previous slide. Okay, credit where it's due. So, I mean, in some sense, this is a formula that's been known for like 100 years. It was reviewed recently in summer school lectures for pure mathematicians. And in fact, the first people to realize that you could do something with this in field theory were the condensed matter theorists, Emmanuel Gull and his group at the University of Michigan. However, the thing that is new or different in this talk is sort of the perspective of what one should make with this arbitrary function. In some sense, the whole excitement is that because you phrased everything in terms of the unit disk, right, the arbitrary function, I mean, it's an arbitrary function from the disk to the disk, but it can't go too crazy, right? It has to be in the disk. And so a question you can ask is what possible values could your interpolating function take if you boldly extrapolate away from these red points to the blue points? So remarkably, you can quantify this explicitly at each point, and the way you should think about this is the size of this set quantifies for you the ambiguity in your analytic continuation from a finite set of points. Okay, so here it is. The answer, it's written in terms of those Neven-Linna coefficients. It's a disk of radius r centered at C of n, and the formulas are in fact extremely compact. The name of this space, like every truly important space in mathematics, has a German name. It's the Werte Vorrat. And so just to say what I've kind of already said now very concretely, this Werte Vorrat gives you a complete characterization of the systematic uncertainty from analytic continuation from a finite set of points. There's no ad hoc regularization here beyond smearing, picking how far above the real axis you're going to go. And there are no model assumptions here. It's all non-perturbative physics. It's analyticity, or phrased more physically, causality. Okay, so far everything was phrased in terms of the unit disk. So you extrapolate here. There's your Werte Vorrat. You undo the conformal map to bring it back to the upper half plane. And if you want the spectral function, that's related to the imaginary part. So you just take the full width and there's a formula. However, better than a formula is a picture, which is often worth 1,000 words. And so let's try to make some pictures for it. To that end, and I promise I'm going to try to finish on time, let's go back to the R ratio. So of course, there's the real experimental data, but in terms of just creating pictures and seeing how a method works, it can be useful to work with a parameterization. In this case, in 2011, Bernecker and Meyer gave a nice parameterization of the R ratio data that hits the rho and the omega and the phi pretty well. Blue are the experimental data, and red's their parameterization. So red's what we'll use as the input for the method, and you can easily move back and forth between R of S, the spectral function, and the Euclidean data, right? Because we've got an explicit curve, and we have the formulas from earlier in the talk. Okay, so what I did is, using those explicit formulas, I generated exact data at beta equals 96, total imaginary points on the imaginary energy axis, and then we're going to do this spectral reconstruction using Neven-Linna Pick interpolation for various smearing widths. Okay, so here's the complex energy plane, and we're going to interrogate what the smeared spectral function looks like at distance epsilon above, and if you do it, the spectral function looks something like that. So there's a hump, and then it kind of dies away. If you do the Neven-Linna Pick interpolation, you find the black points, which are now coincident with those curves, and what you find is that there's actually negligible systematic uncertainty there. If we decrease epsilon to increase our spectral resolution, what you see are these spectral peaks from the rho and the omega, and the phi beginning to emerge as you move toward the real line. No surprise there. The interesting thing is that on the right-hand side of this plot, you see some small but non-zero systematic uncertainty just coming from the fact that I only brought 96 total points to bear on the problem. But other than that, it works pretty well. If I go down even further, you can see those poles coming out even more clearly at modest increase in the systematic uncertainty from the Werte Vorrat. You can phrase the problem a little bit differently, and you can say, all right, let's suppose that I'm interested in what's happening near the peak from the rho in this smeared spectral function. And I'm going to fix some number of points on the imaginary axis. And you can ask, how does my uncertainty from the Werte Vorrat, how does this scale with the number of points I actually use in the interpolation? Right? Roughly speaking, you'd expect it to be decreasing as you add more analytic information. In fact, that's exactly what one sees here on the right. What's plotted is the fractional uncertainty in this point here. And horizontal axis is the number of points used in the reconstruction. It's a log scale on the vertical plot, and this is roughly a straight line, so you can see it's approximately exponentially decreasing as you bring more and more analytic information to bear. And after about 100 points used, that suffices to get, in principle, per mil precision. Okay, so the perspective I want to offer from this is that this Wertevorrat, this special space, offers a systematically improvable approach in the sense that as you add more points, it gets smaller in a regular way for increased energy resolution and spectral reconstructions. It fully bounds the systematic uncertainty associated with the analytic continuation, even when this uncertainty is not small. I want to emphasize that this is just some convex set. It's not a 1 sigma error band. Okay, so those were the 2 data points I wanted to talk about. The third is the reality of statistical uncertainty. There's a lot that could be said here. It's work in progress with Ryan Abbott, a student at MIT right now, and maybe we can chat more about that online. And then just my last slide to summarize. So I began the talk by describing the many important phenomenological applications of processes like these, which range from everything to G-2 to first row CK metrology, to B anomalies, or even to Dune, the EIC, and beyond. I think in the past couple of years, there's been improved practical and formal understanding of some of the challenges associated with these processes, which for many years they were unspeakable at the Lattice conference. And I'm expecting some exciting calculations to come out of this over the next few years. And of course, I haven't had the time to review everything that people are already doing. So with that, thank you.
Thanks a lot. Very nice talk. Arkady, yeah.
I'm kind of trying to recollect from the previous experience. I had that this kind of, you have dispersion relations. And then you are writing real part as integral of the imaginary part. And the part which was kind of important for us was that you can approximate imaginary part by some peak or, kind of a simple approximation, right? And you will get a smooth function for the real part. And the point is that restoring, getting a real part from this imaginary part by dispersion relation is kind of stable problem. So you made minimal, you made some deformation. No, it changes the real part, but it's smooth. But as far as I can say that the inverse problem, reconstructing imaginary part or from smooth part, it's difficult because, okay, small changes in real part, so it's kind of incorrect problem in mathematical sense, I'm not sure that what you're doing is this way, but I'm still trying to find out.
Yes, so several things can be said to that. So the first has to do with sort of the self-consistency of the input data. So imagine you had lots of data, but without any statistical noise, but just computed to some finite precision. It would be good to know before you got started, is this going to work or do you expect it to fail? So this is sort of related to what you were saying. It turns out that one of the hypotheses of the theorem is, this is due to Pick, not Nevin-Linna, is that the data have to satisfy an analytic self-consistency condition. There's a certain matrix that you can write down in terms of the nodes and the values that has to be positive definite. So indeed, things can be sensitive to exactly what you have, but you have some guidance from a condition like this about whether you expect it to fail. And I think crucially from an operational perspective, because it announces before it gets going whether it will fail, you can then push it into regimes where it does fail and see how it fails and then try to develop either techniques based on theorems that will then help you, or at least heuristics that guide it in. The second thing regarding stability that should be said is, although I think it's actually not a showstopper that it's so sensitive in principle to the input data, you should really use extended precision arithmetic for all the intermediate steps. This seems to be kind of a common thread that appears in much of this business. For instance, the HLT algorithm that people are already using, this also requires extended precision arithmetic for the intermediate steps. So, I mean, it's sensitive, but I think there are things to be done.
Okay.
Is it possible to use this technology to compute transport coefficients through the Kubo formula?
I think so.
That would be super cool.
I agree. Yeah, fully agreement. I think it should be possible.
I applied the HLT to a this parallel rate it's possible, right?
I mean, maybe I'll give you a little bit more context rather than just my one-word answer. So, I mean, people at the Lattice community have been thinking about finite temperature QCD and transport coefficients for a long time. I mean, I'm not particularly an expert on that, but my sort of view is that one of the things that's always been difficult is quantifying the systematic uncertainty with various choices that you're made. If you do maximum entropy, you get a curve. If you do some other method, you get a curve. Everybody gets a curve, but what do you do if the curves don't agree with each other, right? And so the thing that's really different about this is that there's really a theorem that says, you know, if you knew those points exactly, it has to be within this convex set and nowhere else. And so I'm hopeful that, you know, in terms of a conversation of ideas, maybe this will be literally what we do. Maybe it will be part of the set of ideas that we bring to bear on it that then, you know, when a transport coefficient is extracted, it then tells you you can trust it or not.
I guess I see many papers on this shear viscosity calculation that people have been trying for years. Do some of these recent papers use this type of approach?
I don't think anybody has used this recently. I mean, I think much of the field theory work that's being done with the Nevin-Linipic interpolation already is in the condensed matter context, and they have a rather different perspective than the one I have, and they're computing band structures, and I confess I'm not a real expert on it. But yeah, that's basically the state of things.
Okay, any more?
I think there's, John had one first, maybe.
I don't know if this is a question for you or for Steve, or some linear combination, okay? But if you try to apply this to a 4-point function, a scattering amplitude, right?
Yeah.
Then in your language, I would think you would do it at fixed t, and what Steve does is at fixed partial waves. So is this another approach to trying to get to the Minkowski space from your point of view, Steve, or otherwise?
I think that this is...
Dispersion relations are usually done at fixed t because you know the asymptotics, right?
So people have thought a little bit about this. It's a paper that I haven't fully digested, although it's just because I haven't spent the time with it, by Max Hansen and John Bulova. They had this sort of LSZ kind of picture for scattering amplitudes that involves smearing. As far as I can remember, it was agnostic to how one smears. And so I think something like this probably works that way. I'm trying to remember what's been done with it or the extent to which they've tried to do calculation. Mm-hmm. Yeah, so I don't know if I can say much more intelligent. Yeah, we might have to measure the other part of the wave function. Okay, Steve's nodding. Okay.
I mean, another thing to think about would be to go slightly less inclusive than the total hadronic cross-section and start putting in some operators like the energy flows that Ian was talking about. Seems like maybe there's a way to do that if you at least take some moments of them or something. It'd be interesting to think about that more.
Yeah.
I haven't related to your question of how much analytic information is encoded in a fixed set of data points. Just based on looking at the plots you showed, is there some kind of sum rule about, for a given number of data points, how well you can resolve a peak compared to how big those error bars are?
That's a good question. I don't know. It could well be that there is, and that might be something else that one could bring to bear on the problem. Yeah, I just don't know.
add what they tried to say before, that at least, I was referring to this, our experience with some rules, right? And their point was that because if you are making model, say, for imaginary part, which is, and it is a correct problem that you are, then you have a smooth real part in Euclidean range, right? But then you are using this knowledge of your real part to fix parameters of imaginary part, because then you are kind of automatically provided analyticity by using this kind of dispersion form of real part, and using real part data to fix parameters of imaginary part. I'm not sure whether it's useful, but I just want to mention this.
The other thing, particularly in light of Steve's talk, that I think is interesting to comment on is, I mean, in some sense, computing the finite volume spectral function, we know perfectly well how to do that. You just do a GVP, you bring a lot of operators to it, you have a big matrix, and then you diagonalize it. And what Steve showed us is that doing this, one can pull off, what, dozens of energy levels? And so in that sense, you could get some version of this blue one here, as long as you're willing to work sufficiently hard with a sufficiently large operator basis. And so I think one of the interesting things that's going to happen over the next few years is people are going to take this smearing perspective and sort of wet it with a variational approach. And that's going to be one of the things that allows us to go out to higher energies with higher precision, and then in a key way, respecting stability. Because, I mean, in some sense, we know that we can get those energy levels already, and we may just be able to get then mileage from thinking about smeared spectral functions and connections with these new observables.
Okay, well, let's thank Will again, and we have a reception and dinner now in the courtyard.